This is Jill Herson. Welcome to our webinar. I'd like to remind everybody that I am recording this session, and the recording and the slides will be available to you by tomorrow, and I'll email everybody with a direct link to the recordings. So to start things off, I'd like to introduce Vinayak Joglekar. He is our co-founder and CTO at Synerzip. Vinayak, take it away.
Thank you, Jill. We are in 2018, and microservices and containerization is the way we will be building enterprise applications going forward. We at Synerzip see this as a big change and a paradigm shift that is happening, and it is worth noting, a change that is worth noting for everyone. Many of our customers at Synerzip are actively building their products using microservices and using containers to deploy those microservices. So today we are going to dive deep into how microservices are useful and what problems they solve, and how it is relevant in terms of putting them in production to use containers. So containerization and microservices are two topics that go hand in hand. So we will be going into those, and for that we have with us our presenter today, Stephen Mason, who is the VP of Engineering at Synerzip. He is based in the Dallas-Fort Worth area. As a seasoned technology leader, Steve worked as a technology consultant and technology advisor to investors over the last several years. He has assisted over 65 companies with systems architecture and technology decisions, operations policy, and leadership challenges. We welcome you today as we discuss microservices and containerization. Stephen.
Thank you, Vinayak. Good to be here.
So, Stephen, for the benefit of the audience, can you just start with why do we use microservices? Why do we even think of doing something differently? Why are we not just continuing to do what we were doing? What is the problem that we are trying to solve with microservices?
Sure. So the large problems that stem from traditional architectures, which we could say classically are monolithic architectures that have a single application tier and a single database tier, they tend to have quite a few problems as they continue to grow. As they increase in complexity, they become more and more difficult to deploy. And even small changes, when you make a small code change, you're forced to redeploy the entire system, which becomes very problematic and often results in downtime. The other element of this complexity is that these sorts of monolithic architectures tend to be highly coupled across components. So for instance, a change in one component may have multiple impacts to several other components. And this in fact makes a large, highly coupled architecture very error prone and very unpredictable. In addition to that, this high density of connections and complexities, it tends to make it very difficult to onboard new developers to get familiar enough with the code base so that they can work confidently and make changes to it. So onboarding with your developers becomes increasingly longer and more involved. And then finally, monolithic architectures are very difficult to scale. So if you continue to operate with a single database, a single relational database, it becomes a very unscalable platform as you grow in size.
Absolutely. I totally agree with you, Stephen. And, there are a couple of other observations that I would like to bring to the notice of our listeners. One of them is that if in the case of a monolithic architecture, if a developer uh, is held up because of some bug or some issue that he is facing, he can hold up the entire release, right? So if you have a team of, say, let's say 12 developers, and one of the developers is not able to commit his change, the release is held up. So 11 developers work doesn't go into production. So that is a wastage that we can save by having uh, them work independent of each other instead of ending up working together as a big team. And the second thing that Stephen, you also talked about is scaling. Now about scaling, one thing I would like to bring to the notice of our listeners that Stephen also said, but I would like to amplify a little further, that let's say if you have a service that needs to scale in a monolith, there's no way that you can create multiple instances of that service and have only that small part to scale. You'll you'll need to you'll need to have multiple instances of the entire monolith to have that particular service scale, and this happens very often. You have bottlenecks, and those bottlenecks are the only small portions of your application that need to scale. So, Stephen, I have one thing that I want to ask you, that how do these microservices work? I mean, it's all good to say they will solve these problems, but how do they actually solve these problems, and what is the architectural approach? Can you talk a little bit about that?
Sure. So microservices encompass a collection of different principles. And now these are all kind of arrived at in an evolutionary fashion throughout the industry, but there's a kind of a growing consensus that certain principles are definitely part of what are considered microservice architectures. And this is becoming increasingly clear. One of the first ideas is that microservices own their own data. This means that each of them have their own persistent data store, whether that's a relational database or a key value store or flat file, but they all own their own data and the data that's relevant to the microservice. A second principle is that these microservices are aligned with business functionality. That means that it's easy to conceptualize what elements the microservice is responsible for in terms of does it execute a particular workflow that a business user would use, or is it encompasses a single application for the business. And the beauty of it being aligned with business functionality is that a single product owner can be assigned to it, and his ideas will be fully realized within that single microservice in a very sort of natural fashion as ideas come through the business. A third principle of microservice is that they are independently deployable. This means if you make an update to a particular microservice, you don't have any compelling need to redeploy other microservices in the production environment. So you can make a small change to one individual service without making any other changes or redeployments to other services. This makes deployments generally to be very small, incremental, and less impactful. So you'll see much fewer incidents of downtime, and if you do, you'll see maybe one service out of production instead of many. Other concepts are that they're fault isolated and encapsulated, which means that they're very loosely coupled to the other microservices. Now, certainly there's a need to share data between them in some cases, but those are done through API calls, and usually there's only a handful of different API calls that connect to microservices. Finally,
Hey, before you proceed, I have a couple of questions, Stephen. First off, you said that microservices own their own data.
yeah.
So does this mean that you have a database that is owned by the microservice and it's not shared? That it's not the like you don't integrate using the database as the integration layer. So the two microservices will not communicate with each other using data in the database, but they will communicate with each other using RESTful API calls. Is that what you said?
Yes. Yes. I mean,
Yeah. Then in that case, how do we, how does one, like if you have a transaction and the transaction is supposed to make changes or supposed to touch two microservices, in that case, how does one ensure that the data is, in the two separate databases is consistent and, how does it follow the ACID properties of a transaction?
yeah. So when you look at that, say you have an update. Let's give an example of a simple auction site in which you have two microservices, one for buyers and one for sellers. As a seller posts a listing, that would be entered into the seller's database for that particular microservice. And then an API call would reach across from the seller service to the buyer service. And then the buyer service would go and enter that listing, or at least a reference to that listing into its database. Now, as you can see, that because of those calls, you remember Brewer's cap theorem that you can't have consistency, availability, and partitioning all at once. So even with microservices, we have partitioning and we have availability of both services. But what you do is you sacrifice a slight bit of consistency for those brief moments that it takes to move that data or enter the data from one microservice to another through the API call. So in most architectures, that's a compromise that can be made with little issue. But there are certainly ways to architect around it if you have transactions that are very time sensitive.
Right. So let me repeat my understanding. So what you're saying is that, since these are two separate microservices, they have to be, and two separate databases, they have to be partition tolerant. So for the listeners, we are talking about the CAP theorem, where you can either have consistency and availability, or availability and partition tolerance, or partition tolerance and consistency. You can only have two of the three. You can't have all three. So what Stephen is telling is that in the case of microservices, these are AP. Consistency is something that is eventual. So which means that there will be a few brief moments when the data that the seller has shared, supposed to have shared with the buyer would not be able to see that data. It would be visible to him only after some finite amount of a few milliseconds, if you will. So that is so how does how does that happen? I mean, do you have some kind of cron job that runs, keeps checking if there has been an update, or what is the way that the data would go from seller to buyer if these two are, let's say, two separate databases with their own servers or own containers?
I feel that you could do it on an event basis. So just as an entry is triggered in one service, that event would also trigger a call from that service to another one. There is also the possibility that you could have a periodic polling from one microservice to the other for updates. Typically, though, you would want to ensure that the services communicate asynchronously or such in a way that one won't hang if another service is down. So if I send out a call, I don't stop the functioning of my service until I receive a reply. I actually send the call, and then the response would go in a queue, and then I read the response from the queue. So those are a couple of ways you can communicate between the two.
Right. So microservices and asynchronous way of communication using queues, message queues, such as the Kafka message queue service or the RabbitMQ message queue services, the way we ensure that we don't have blocking calls and we don't have services waiting on each other. Instead, events are so what we the terminology that for the benefit of our listeners that we use is event sourcing and CQRS. So event sourcing is where, as Stephen was explaining, you have an event taking place such as a seller updating data, and that event is posted on a message queue such as Kafka or RabbitMQ, and then the buyer service will in turn pick up that message, and for which seller won't be blocked. It won't be waiting for buyer to pick it up. So buyer would pick it up eventually and add that to its own database. So that's how event sourcing works, and we would talk a little bit about that later. So there is an associated concept of CQRS, wherein you have two types of services that write and update data, and services that read data. So uh, you know so why do we CQRS stands for command query segregation. So command query responsibility segregation means the essentially in layman's term, as I understand it, is that you have databases which write are separate, and the calls which so the you have separate services that will deal with updates and writes, which are infrequent, whereas reads are more frequent. So you have separate services to do only reads, and if a service that reads is something that is immutable because it doesn't have state, so it can easily scale. So that's the principle behind CQRS. So to talk a little bit more about CQRS, so what we do in that case is we have pets and cattle. So pets are services that can that need to be looked after, and cattle are services that we can kill, and that makes it fault tolerant. So read services being cattle, and write and update services being pets, they need to be looked after. So so much for the segregation of CQRS. Now, you also talked about the monitoring, right? So can you talk a little bit about what is the importance and why is it easy to monitor? I think it would be easier to monitor if I have let's say a monolith in which everything is in one place, and if I have things spread all over, why is it easy to monitor?
Well, it's you have much more granular information on the health check, the microservice, and when we talk about containers later on, we can discuss that a little bit. But the idea is that that each of those services, will give you a sense of whether it has a healthy status, and then also you can listen and monitor for how many transactions that particular service is taking over a period of time. What that gives you, though, is a real good sense of where issues may be within your architecture or where they start. contrast that with a monolithic architecture. Because you have that steep interconnection, the highly coupled components, it becomes very difficult to disentangle what element of the system is impacting another one. And while you may be able to detect an error, it's going to be very hard to go ahead and narrow down where exactly the source of the bug is coming from that's causing it.
Right. So, you're saying, what you're saying indicates that you're dealing with something smaller than a monolith, but how small or how big should a microservice be? So let's say I have to build a microservice. So is it something where everything that goes into the buyer side of e-commerce would fit into one service, or is it something smaller or something bigger? So can you give some idea about when you're deciding what should go in a microservice, how big it should be?
Yeah, sure. So how big should a microservice be? This is a point of quite a bit of discussion. And in fact, many architects feel that the prefix micro is a bit misleading, that you can really embrace these principles and services that are of decent size, but make your architecture much more robust. So if you have a large number of services, there actually is there becomes a bit of overhead both with monitoring and deployment to bring those to production. And so that can become a problem if, say for instance, you had hundreds of microservices, which would be kind of an extreme case. If you have too few microservices, you begin to see all those monolithic problems rise again. So unfortunately, the answer is it's fairly specific to the application you're running. Now that said, there are a few rules of thumb throughout the industry. Different companies do different things. One is, one rule of thumb that's kind of spread around is this service small enough to have been built in a working MVP fashion within 2 weeks? And so those would be relatively on the small side if you can build this service in 2 weeks. The second a rule of thumb, this actually comes from Amazon, is it should be no bigger than can be run by a 2-pizza team. So essentially a Scrum team of no more than 8 people have to be able to run and maintain this service. So that would kind of be on the little larger side of a rule of thumb for microservices. I like to go with the idea that the size really facilitates quick onboarding of developers, and also being able to make and update changes with a high level of confidence, and that requires deep familiarity with the code base. So if you can onboard a developer to work on a particular service in 3 weeks or less, and that developer can then make changes independently without necessarily having a code review, then I feel that that's probably a good size for your services. But I wouldn't go too much smaller than that.
Yeah. So Stephen, I have been reading on this topic, and I read some time back a book by Eric Evans, right, which talks about the concept of it's the name of the book is Domain-Driven Design. And this talks about the concept of bounded context, wherein what he says, and this may sound a little theoretical to the audience, and it does sound a little theoretical to me as well, that the concept of bounded context is that when you have a organization, and in that organization you think of a workflow or something that happens in a context within the company while you're building an application, your microservice should restrict itself to that context, so that like for example in a warehouse you have a particular clerk who's receiving various items that are being brought into the warehouse. So he is just doing that one function, right? So he has this invert document that comes in, and he's just handling that, and that is his bounded context. So your microservice should be visualized as something wherein in an organization, if you have a separate small part that, so I have just read about it. I have not actually built microservices in that fashion. But what do you think? I mean, is this the right way to think about things when you are building microservices?
Yeah, absolutely. And I feel that this idea of bounded context really dovetails nicely with that principle of microservice encompassing business functionality. So the way that I conceive of it as you really begin with a persona of a user. In that, in the infancy stages of your architecture, you build to the needs of that particular persona. So this is a real simple example here with, an auction site where you have buyers and sellers. So if you can imagine, as you initially build out the architecture, you may have a buyer service, and then you have a seller service. And as those, as the architecture kind of grows in complexity and size, and you get beyond where you can service it with a reasonable sized team or onboard developers in a reasonable amount of time, you say, okay, well, let's fork it into the sort of business functions or tasks that the buyer will execute. So for instance, buyer side may be split into search listings and then on the and bid on items, whereas the seller microservice may then be split into two microservices like create listings, monitor listings. The real advantage to this is that it all kind of comes together at the organization level, because the product owners typically are non-technical individuals, and they look at their user stories and the feature creation very much from the perspective of the user persona. And so when they come up with an idea, it's something that impacts the buyer's experience or the seller's experience. And when they give that to a development team with which they're associated, that development team should really, in most cases, be able to craft and create that feature without having to cross-coordinate with the development team who's working on seller. So as we have this sense of bounded context, in alignment with business functionality, that keeps those ideas flowing very fast, and lets you to kind of improves your time to market as you begin to build out your architecture.
So Stephen, what you're telling me that like what I've been doing for the last 2 decades of my life needs to change, because what we've been doing is typically building teams the architecture has essentially been horizontally sliced. Like we have the front-end guys, and then we have the database guys, and we have the middleware guys, and these teams are like, cutting across all the functionalities, whether it's buyer, seller, search, bid, create. So everyone is dealing with everything. Front-end guys are building your front-end using, React or Angular, and the back-end guys are using the databases, and and the middleware guys, of course, are using Spring and Hibernate and all the. So these three things, 3 layers are what is kind of, I have got so used to it because we've done this, for like 2 decades, as I was just telling. Now, what you're telling me is that the team now is not going to be that. I mean, the team now is going to have all layers. So there will be people who will be handling everything from back-end to front-end as full stack development, and they'll be doing only just one thing like search or bid. Is that what I'm hearing?
Yeah, absolutely. So that transition from a functionally aligned and grouped organization where you have all the product owners working together and all the user interface folks working together, and then devs collected in QA, where you have them in sort of separate silos of the organization. That may have been appropriate for the decades where you're releasing packaged software on CD-ROMs or something like that. But really, to make very speedy, effective changes, you really have to go with the new SaaS products. You really need to go with cross-functionally aligned teams because they're able to execute much faster and get to deployment much faster than you would in sort of that functionally aligned organization. And that's becoming an increasing realization throughout the industry. Some organizations that embrace that really you'll see are Netflix and Amazon. Amazon's classic for their sort of eight-person teams that each run a particular service. But you also see that the speed of innovation is much faster in those small teams.
Yeah, I understand. I understand that you have cross-functional teams. You have you have developers, QA, DevOps, UX, and all that. But what I also understand is that they would now be able to build something meaningful and deploy it and get feedback from their end user, independent of any other team. So it's like a team kind of building an application all on its own, right from the database to user interface, and actually deploying it independently and getting feedback from their end users. So that I think is very exciting, and I think this is something which is what makes this concept of microservices very powerful, because now you don't have to wait for months to get the end user feedback. You are going to as things get ready, you're going to get the end user feedback and incorporate that feedback. So getting early feedback is definitely going to save a lot of trouble that one has to go through when I have had several instances where we have built some functionality which is launched with a lot of fanfare, and when it goes out in the market, it really is not what the user wants. So here's something which you can do kind of micro releases very frequently and get frequent user feedback. So I think that is very exciting. But to do that, we need to deploy it, right? I mean, you can't just build it. So that I think is a question that I have for you, Stephen, that how does one deploy these things? I mean, these things are deployed in containers or on virtual machines, or how's that happening?
Yeah, so as we move on to containerization, containers are sort of a natural fit of technology that works very nicely with microservices. Now, there are two different concepts and ideas. Certainly, you can have microservices without using containers, and you can have containers without building your architecture in microservices. But the two complement each other in a very nice fashion.
Right.
Should I give kind of a...
Yeah, so containerization is something that, sounds more like, so what is the difference between a container and a virtual machine? I'm not very clear about that. So can you just explain it a little more in detail?
Sure. So to give a little bit of history, virtualization became possible and also very popular as servers became more and more powerful. So if you can imagine about 10 or 15 years ago, servers were becoming more and more powerful, and this idea of hey, can we virtualize a machine, or can we emulate one machine on top of another machine? A lot of data centers had sort of excess capacity, and they wanted to see if it was possible to run multiple OSs on a single physical piece of hardware. And what this would do would save them money. So, for instance, if I had a machine where I'm running a Windows or IIS, and then I also wanted to run a Linux machine as well, I wouldn't have to have two physical pieces of hardware to do that. I could have a single server, powerful server, and then have a virtualized a computer on each, one running Windows or IIS, and one running Linux. So this made it pretty efficient and cheaper to run data centers. Also, this idea, and so this is what's traditionally referred to as virtualization, and this really made the cloud possible, or the public cloud possible, because of the sheer economies of scale and the ability to move a virtual machine from one physical machine to another very quickly. It made it cost effective for folks to have large public data centers where anyone could subscribe and then spin up their own VMs.
So yeah, that's okay, but what is that got to do? I mean, how does it give me, what are the advantages that I have of virtualization for deploying microservices? So that's what, like, I want to deploy microservices in a very quick and easy way where I can spin off a new microservice instance quickly. And when I need to just shut it down so that I don't have to pay for it all the time. So it sounds very interesting, but how does it actually work? Do you have a virtual server on which you deploy a microservice, or and then how long does it take? And then when I shut it down, how long it will take to bring it back? Does the user have to wait for it to come up? So can you just tell a little bit more about how it is useful for deploying microservices?
Right. So a typical VM, it's possible to provision within a matter of minutes in the public cloud. And that's really just the time to go ahead and boot the OS. So for instance, if you were just using virtualization or VMs for a service, you could potentially have one up and running in a few minutes. Now, when we talk about containerization, which is it's also virtualization, but it's a very specific improvement on it. These containers can be spun up in a matter of seconds. And the reason for that is that containerization is similar to virtualization, except that the OS is shared amongst several containers. So, for instance, your application or your microservice would live within its own container and would have its own resources dedicated to it by the OS, but it would share that particular OS instance with potentially several other containers. And in doing that, we no longer have the lead time of the need to go ahead and boot the OS up. So containers, which are much smaller, can be moved around from one OS to another. They can be started and stopped within seconds. And that provides a very responsive and scalable environment for peak usage times.
You had a picture you had shown me some time back. So, I mean, can you just explain this? I mean, it's hard to understand without seeing a picture.
So this, I believe, is the one you're discussing. When we look at virtual machines, what you see is you have the host hardware at the bottom, and then there's an operating system, and then there's a layer called the hypervisor, and the hypervisor manages or provides the environment to support the multiple virtual machines that are working on top of it. Each of those VMs has a full guest OS. So this could be IIS, or it could be a version of Linux or some other operating system. And then there are multiple applications that are working on top of this. So if you deployed your microservices in this fashion, it would be fairly resource intensive because you'd be consuming quite a bit of resources for each individual guest operating system. When we look at containers on the other side, again, you have the host hardware and the host operating system, but then you have the Docker engine. And this diagram is probably not the most perfect because the Docker engine actually sits alongside the various microservices as another application, but it serves to orchestrate the containers that are in production. And each of these applications, again, has a fairly limited resource footprint. So you're able to pack many more of them on a particular machine. If you can imagine, it's sort of like with virtual machines, you're packing a moving truck with really large boxes, and with containers, you're packing a moving truck with very small boxes. So you're actually able to take advantage of all of the resources that are available on a machine, whereas there is some waste on sort of a virtual machine. So you have a much more efficient model with containers.
Yes, I can see that because there's a lot of things that are common in the operating systems. So you have, for example, you're maintaining a file system, you're maintaining a thread pool, and you're managing various services that are needed for operating systems, such as memory management and garbage collection, all that. So all those services are common, and they can be shared across containers, whereas in virtual machines, these are not shared. So each one is carrying its own operating system, which is a lot of heavy lifting. And that's one reason why I can imagine that it takes a lot of time for a virtual machine to get started. Whereas, since you don't have so much heavy lifting required for bringing up a container, you would probably bring up a container within a matter of a few seconds as compared to a few minutes in the case of virtual machines, and which is why it makes it so much more efficient and effective, because as the scaling requirements come up, you need to spin up additional instances of microservices. Within a few seconds, you have additional instances made ready and available for users. And as the user's demand goes down, they can be shut down, and resources can be freed up equally quickly. So this makes a lot of sense. But how do you manage these containers? I mean, isn't it? How do you make sure that they start in a particular, because they're sharing, so they need to start in a particular sequence, and then they need to collaborate with each other, and there needs to be some kind of environment in which you can run these containers, right? So is it Docker that provides that environment?
Yeah, so I think what we're referring to is this idea of container orchestration. And there are quite a few tools. Docker Swarm and Kubernetes are perhaps the most common, and they provide a number of functions for containers. So one is providing a sort of directory service for one container to know where another is located, so it can perform calls to each other. It also, the orchestration also involves deciding if you launch one container, you may need two instances of another container also launched at that same time of a different service. Containers are always launched as images. So the orchestration engine has a full image of the particular container. and deploys it, and it's deployed in an immutable fashion. So there are no patches or changes applied. What happens is if you update a particular piece of code, Kubernetes will then pull from that repository and then redeploy the whole image. So all deployments are immutable in production as well. But all of those functions are maintained under this idea of container orchestration.
Yeah, so Kubernetes and Docker Swarm is what I see here in this picture, and I've also heard about mesos. So there has been a lot of discussion and talk about these three competing standards. And of late, what I have seen, and as you were talking, Stephen, you were keeping using Kubernetes more frequently. So for the benefit of listeners, Kubernetes has already evolved as the de facto standard, and it has won the container orchestration wars, if you will. And today, there is so all cloud providers, service providers, be it Google, Microsoft, or Amazon, all of them are providing out-of-the-box implementations of Kubernetes on their cloud. So you would be able to deploy containers onto Kubernetes, irrespective of whether you're working with Azure or with AWS or with Google Cloud. So that is something which that's a big change that has happened. I mean, you don't no longer have to invest your energy in comparing various technologies which are competing with each other, and then you don't have that risk of ending up in something that doesn't go forward. So that's a big change that has happened, and Kubernetes being supported by Google is definitely a winner. So that brings us to the new world, wherein we have a lot of new applications that are being built on top of Kubernetes, and which means you have whether it is monitoring or logging, or you have service discovery. So everything that we used to think of as something that is required in microservices architecture is available out of the box and pretty much standardized. So as Stephen was saying, these things are they have a stated state, and it achieves that state. So if there are, let's say, 12 instances are desired, and then you actually configure the desired state that a particular service needs to run in 12 containers in 12 instances, and by some chance something happens to one of those, it is it automatically spins up a new one, and you don't have to. So Kubernetes takes care of ensuring that your desired state is always maintained. It will go to your AWS cluster, go to spin up another instance of a node if required, but it will ensure that the total number of containers that are configured in the deployment is always maintained. So that's how scalability has become very easy to have, and it's something that helps us to maintain uptime and keeps our users happy. So all this is good, but combination of, now coming back to, we talked about microservices, we talked about containerization and deployment. Now, can you tell us what is the combination, the advantages of having microservices being deployed in containerization? So, and what are these two topics a little bit of clarity on how they are different or similar.
Yeah, so microservices, is truly an architectural design pattern, whereas containers are a deployment technology. But the two of them make sort of a natural complementary fit. Generally, both microservices and containers are, encompass processes that are smaller and less resource intensive. They also enforce this idea of loose coupling. So if I deploy a microservice within a container, it actually has to make a call outside that container over the network to another service to communicate with it. They're both independently deployable. So containers sort of embody, all containers by themselves are independently deployable. So they sort of embody that principle of microservices of being independently deployable. And then also with the orchestration tools, part and parcel with that is enhanced monitoring of the individual microservices.
Right. So, do you have, any idea about, how it is possible? Because I can't imagine monitoring, let's say, hundreds of these microservices which are running on different servers. So, if one goes, so how does one, how is it, how is it easy to monitor? I mean, I can understand if I have a server on which a monolithic application is running, monitoring is easy. I can just look at the logs there on that server, and probably I can keep looking at the logs and I'll know everything that is happening there. But imagine if I have a distributed system in which there are a number of logs that are running on different servers, and I don't know where to look. I mean, how do you monitor, and how is it making it easy to monitor? This is something which is hard for me to imagine.
Well, so all of those, the start and stop of individual services as well as their resource utilization and health are all aggregated with the orchestration tool. So you're able to determine, what particular container or collection of containers is having issues at a given time. So very, very much as you had said earlier, or we had discussed earlier, it's really about not just knowing that there is a problem, but identifying specifically where the problem is within your architecture of what particular service is failing.
Yeah, so you have aggregation of logs, which means that from each container there is some thing that is sending the logs to a central server, right? Or some central place where all the logs are being aggregated, right? And that's where I have a question that then there will be a proliferation of various logs coming at different points of time from different servers doing different things for different sets of users. So how does one make sense out of these millions of log entries that are, coming in a random sequence are being thrown at you? So how does one monitoring means you'll need to make sense out of these things that, let's say if I have a service going into a particular service call, and then A calls, B calls C, and then D returns the response to the user, in which case, how does one bring traceability? Because you will be having logs coming from service A, B, C, and D, and then they are being aggregated, and then you're, you have several, they're getting intermingled with several users' logs. So is this something to do with, having some kind of correlation ID that keeps track of these across multiple calls?
That I personally not is familiar with. I'm not sure if you had.
Yeah, so what I have known as that there's some kind of correlation ID that gets spawned off when a request hits, and then you have that being maintained along with the log entry. So when you aggregate all the logs, for every service from A to B, B to C, C to D, you have those, you can filter all other logs based on their correlation ID, and then correlate those logs which pertain to a service call, which which makes it easy for you to uh, track. So that is what I've heard. But then I think there's more to it than what I just said, because these things are more complex, and because there are multiple instances of the same service, so it is not that simple. But I think that's the high level idea that I have heard about, Stephen. So Stephen, before we end, we are coming close to the end of the hour. We have just 5 minutes left. I would like to ask you, if I have not asked you something, is there something that I should have asked you which I didn't ask?
I think that I think we've covered the majority of it. I'd be excited to hear from the audience what their questions might be.
Yeah, so we will wait for the audience, so let the audience come up with questions. In the meantime, Stephen, can you walk us through the Synerzip introduction and how Synerzip is working on microservices, and a little bit of excitement that we have here? Can you share it with everyone?
Sure. So Synerzip is your agile software development partner. Who we are, we're a company with 500 plus developers. We've been in business over 10 years, and we have sort of a dual shore model between India and the United States. We focus on we use the most modern development practices. This includes DevOps, lean startup mentality, and we work to accelerate and automate your processes, including QA and testing. So we're very forward-leaning in terms of our methodology. Dual shore operations in the United States, we have our customers and some of our senior architects. And then the India team, we have a collection of developers, QA professionals, and product owners. And we like to extend your existing team to serve as your India development partner. We have quite a few companies with whom we've partnered in the past. These are probably some of our larger names that we've worked with. And we've had over 150 clients.
So I have a question, Stephen. So the question is, if I have a large monolithic enterprise application, do I rewrite starting from scratch, or how do I migrate from such an architecture to a microservices architecture? What is the path that I should follow?
So I would be very hesitant to rewrite any architecture from scratch in sort of a big bang fashion, particularly a very mature architecture that has quite a bit of complexity and user features. Generally, what I would look to do is look for a set of functionality that's largely decoupled from the rest of the architecture, perhaps a service that's primarily read-only, or something like search. And I would look to rewrite that particular functionality as a standalone microservice and begin to split apart the data model in that fashion. Once you've broken out a single microservice, then I look for the next most decoupled element of the architecture and to see if I can split out a second one. What this does is it allows you to kind of progressively adopt microservices, but avoid a sort of big bang transition, which usually doesn't turn out very well. And it also, as you slowly chip away at these different functions, you're also progressively simplifying the data model underlying it until eventually you're able to rewrite the core element of your previously monolithic architecture.
Wonderful. Stephen, and I would like listeners to note the word something that is isolated, something that is as decoupled, the word used by Stephen, decoupled. So, which means that you should not go for building something which is at the core of your enterprise functionality. It should be something that is peripheral. And, what Netflix did was they started building their first microservice with their job board, which was not a part of their main video streaming functionality at all. So that's how we should start building microservices. And we are right on top of. In fact, we are a couple of minutes after the time that was scheduled. So I think I should stop here. I should thank. So thank you, Stephen, for your wonderful and insightful sharing of your slides and your experience with us. And it was a pleasure to have you here. The recording would be available soon for everyone. So thanks a lot for being here with us today, Stephen.
Well, thank you, Vinayak. It was a pleasure as well.
So our next webinar is going to be on another exciting, even more exciting topic, that of blockchain application development. And the presenter is Glenn Jones, an old friend and associate of mine who is the global product and R&D executive of SweetBridge. The date is Tuesday, 10th of April, so make a note of that date at noon Central Time. So make sure that you register and get to attend this wonderful webinar by Glenn Jones. Thank you very much. Thanks for coming here and attending our webinar. Thank you for your support.